It is my pleasure to welcome you to the opening series of the Astronomy and Physics Colloquium that we keep every week. And it's my utmost pleasure to welcome you to an exquisite event. We are hosting today a NASA representative, Dr. William Borucki, from NASA Ames Research Center in California. He's visiting us here to tell us about one of the hottest missions on the block. This is the Kepler mission. The Kepler mission's main goal is to find Earth-sized and Earth-like planets that revolve around stars outside our solar system, so these planets are called extrasolar planets. Before I invite Mr. Borucki here to give us his presentation, I would like to spend just a couple of minutes to introduce him. His career started in 1962. He got his master's degree in physics from University of Wisconsin-Madison. He worked in rocket science from the very beginning. He built model rockets since he was a child. And obviously, his career took him to build bigger rockets that we use to get the data. He worked on the Apollo mission. He was working on thermal shields on the Apollo missions, and you know that the Apollo project was a huge success. We landed on the moon, and Bill Borucki was an integral part of it. What followed later, because Bill's extremely versatile, I've known him for quite a number of years now, working with him on Kepler. He wasn't happy to be focused just in physics. He branched out into biology, meteorology, and he got a master's from the University of San Jose, California, in meteorology. He worked on planetary atmospheres, mostly the influence of nitric oxides and other gases and the influence on ozone, and trying to understand the physics behind it and the implications for extrasolar planets as well. In 1984, the saga of Kepler had begun. I am sure that Bill will tell us quite a bit about it. He has been the principal investigator of this mission since its very conception, and in 2009, we were together at Cape Canaveral to witness the launch of this extremely successful mission that has, to this date, discovered, or unearthed, I'll say, more than 3,000 candidates. And just as a comparison, a few years ago, before Kepler was launched, this number was nearly 300. So we are an order of magnitude richer in the population of extrasolar planets, thanks to Bill Borucki and the whole Kepler team. So please help me welcome Bill Borucki.
He has played a major role as well, because when we look at these stars, we see eclipsing binaries. Most of the stars, in fact, in our galaxy are binary stars, and I'll talk about that a little bit later. What I'd like to talk about today is the question of are Earths common or rare, and how do we go about answering that question? I think Andre did a very, very nice job of introducing the objectives. The idea is to find the frequency of Earths. Are they frequent or are they rare? If they are frequent throughout our galaxy, there's probably a lot of life in our galaxy. They might be just waiting for us to use our radio telescopes to call and say, hey, we're here, we'd like to join the club. On the other hand, if we find none, that's quite a different story. That would be sort of tragic. If we found none, there's no places for life, there's no Star Trek. That would be a tragedy. Okay, so we're trying to determine the frequency of planets. We're trying to understand their size distributions, how many are like Earth or like Mars and so on. What are their distances from the stars? There's some major axes. And associate those results with the kinds of stars they orbit. Stars look like they're little dots in the sky, but they're much, much more complex than that. They have different compositions, they have different ages, they have different sizes, they have different temperatures. So if we can do that association we can look throughout the galaxy and see where there are likely to be lots of other planets. I always like to start with the idea with a paradigm. Here's what we imagine and how the facts fit into this paradigm. This is a paradigm of how our solar system formed. And we know in our galaxy there are lots of giant molecular clouds that every so often one or more of them gets disturbed, usually by a supernova event, for example. A portion gets compressed, and material starts falling inward under gravity, and as it does, it maintains its angular momentum. So it's like a skater pulling her arms in and spinning faster and faster. So this material falls in, spins faster and faster, becomes a disk of dust and gas, like shown here. And it's forming, the center part forming the star, the outer core are forming some of the planets. So when a star forms, planets form, which is important and quite different than what we thought about even earlier a century ago. That means that since the gas is all rotating together, you expect all the planets to move in a prograde orbit. They're all going in the same direction. That's what we find. We explain our solar system nicely that way. If you look at the spin axis of the sun, it's perpendicular to that orbital plane. The spin axis of the planets are also lined up in that fashion as well. So we can explain that. It's not true for all planets, but for most planets. Similarly, if the planet it gets formed close to the star, it's formed where the gas and dust is so hot that you can't condense ices and things like that. You can only condense refractory materials, rocky materials that would form Mercury, Venus, Earth, and Mars. Further out in that disk, it's cooler, and the disk is bigger, so you can form bigger planets. That's where you expect to find the Jupiters and Saturns and so on. 5 astronomical units, 20 astronomical units further out. An astronomical unit is the distance between the Earth and the Sun, some 93 million miles. So this is a nice explanation of what we have. The orbit's going to be circular, everything goes around together. Jupiter's where God made them, they're out at 5 AU or 10 AU, where they all belong. Unfortunately, we went out and made some observations. And what we found was just everything was a surprise. In particular, as our technology developed, we could find Jupiters. We found Jupiters. Our first Jupiter had an orbital period, not of 12 years, but 4 days. Inside the orbit of Earth, inside the orbit of Mercury, inside, as close to the stars you could imagine. And after that, we found lots of other Jupiters with these short period orbits, indicating there was more to planetary formation than we had imagined up to now, that we had imagined in developing concepts of our own planetary system. And so we'll talk about some of those things. In particular, we've got to explain why we see many large planets, that are close to the star. How did it get there? How could you have a giant planet which needed all this material so close to the star? Well, there's very little material to build it from. And the answer really is, well, think about that disk. That disk means that a planet's forming in it is going to be interacting with that disk. And in fact, the next figure is a supercomputer program result that shows what people are finding when they simulate this. To the left is the star. It's not showing on this, but the star is off to the left somewhere. And there's a disk around it of dust and gas. In that disk is a planet forming. Inside that little ellipse is a planet forming. Now, a planet is denser than the dust and gas around it. It's not what we call pressure supported, so it's moving faster. Moving through the gas, no matter where it's at, it moves faster than the gas does. Now, it's leaving a wake. It's making a wave in this dust and gas as it passes through. That's very much like a powerboat going across a lake. The powerboat goes across a lake and you see this wave stream out from under it. If you shut the motor off and run out of gas, the boat stops and the wave disappears. The wave is abstracting energy and momentum from that boat, from that motor. Difficulty is the planet doesn't have any outboard motor or any other kind of motor. So what does it do as it loses energy to the wave it generates? And the answer is it loses potential energy and it spirals into the star. And so what we see here are planets forming in this disk and migrating in toward the star. The wake here looks rather strange. It's not V-shaped, and that's because the outer disk is moving very, very slowly and pulling the wave back. Similarly, the inner part of that disk is moving very rapidly, more rapidly than the planet, so the wake actually precedes in angle the planet. So the real question is going to be, well, what stops this planet from falling into the star? And we'll talk a little bit about some of our ideas there. We also want to talk about the habitable zone. The habitable zone is sort of a broad concept here, and it's sort of shown here a little bit. You can imagine some stars. You can imagine that the planets around one of these stars, it's so far out, it's out in the blue, where everything is so cold. The oceans are frozen. They're forever frozen. The planet's forever frozen. We don't think life is likely to evolve there. Or it could be in the red zone. You're so close to the star, the oceans boil. The water goes into the stratosphere. The stratosphere has ultraviolet pouring down upon it. You split the hydroxyl off for the hydrogen and lose the hydrogen. The hydroxyl diffuses back to the surface, and you get a red surface like on Mars, but no water. What you're interested in is the region between the fire and the ice. You're interested in the region that's green, the region where you might have liquid water on the surface of the planet. And that's where we're looking. And so you can see from the diagram that if you talk about a cool star, that's close into the star. If you're talking about a hot star, that's quite a ways out. And that's representative of the orbital periods. You need to look at a planet for several orbital periods before you say, aha, that really is an orbital, that really is a planet, or at least something orbiting a star. It's not a spot on the star. And spots are certainly as big as planets. Well, you know, this should be an easy job. We should build a big telescope and go look at all these planets. It doesn't work. And the reason for that is that the star is about 10 billion times brighter than the planet. That means when the light comes in the telescope, it scatters around the system and completely overwhelms the light from any planet. You simply cannot find a planet that way. So what we do instead is look at the light from the star and say, how is that affected by the presence of the planet? Well, the planet tugs the star, and so the star is wobbling around in the sky, astrometry. It's moving back and forth. You can see the Doppler change in its color. That's radial velocity. And if the planet moves across the star, transits the star, it blocks sunlight. So when you're measuring the brightness of that light, you see the star dim for a while, and then that repeats again each orbit. The amount of dimming, of course, is the size of the planet compared to the size of the star. We know about the star's characteristics, so we know how big that planet is. We measure the orbital period. If it's very short, this thing is too close to the star. If it's very, very long, too far away. We can use the orbital period, Kepler's third law, and the mass of the star to get the distance of the planet from the star. We can measure the temperature of the star, get at the size of the star, and we can calculate the radiation incident upon the planet and get some measure of whether that planet is hot or cold or just right. What we're doing here, however, is looking for transits. We're looking for shadows. What's the probability that you have a planet in a particular orbit that you'll see it? The orbits are all randomly oriented in our galaxy. And the answer, well, it's proportional how big the star is. It's inversely proportional to what the orbit is. And that is how you calculate the geometrical probability of an alignment. And that probability is like 10% for orbital periods of a week or less. But out at 1 astronomical unit where the Earth is at, that's 0.5%. So this method is actually a terrible method. If you point to some star and say, does it have planets? For all you know, it could have 30, 40, 50 planets. You wouldn't see them because the orbits might be aligned perpendicular to your line of sight. But this works great if you say, I'm going to look at 100,000 stars. 0.5% times 100,000 stars, several hundred planets. You see several hundred planets? They must be frequent. There's maybe lots of life out there. If you see 0, the opposite must be true. So we're going to do transit photometry, and we're going to have to do ensemble photometry of thousands of stars simultaneously. It won't work for a few. If we're looking at all these stars all the time, and particularly these stars are much like the sun, we can learn about the sun. We've got lots of examples. We know, for example, that the sun every so often, say in 1670 to 1700, didn't have any sunspots for 30 or 40 years. At that time, the Earth's climate became very cold. The glaciers began coming back down out of the mountains, overrunning some of the farms in Europe. This ice age, little ice, I shouldn't call it little ice age, it was the Mulder minimum. And there was a similar minimum 300 years prior to that. And so we'd like to know when the next one will occur. And we don't know that, we don't understand it, but by looking at other stars, we might be able to recognize precursors or learn something about the mechanism of when we might expect the next such event. Okay, we're going to watch a little planet move across the star. Here's a great star that we all like. It's the Sun. And you can see there's a solar maximum ejection event occurring where you have this enormous amount of material hurled out of the Sun. And of course, when it hits the Earth, you have these big magnetic storms and problems with electrical grids. The Earth is there to scale, and we want to watch this thing track across our star. Well, the star is so variable, so noisy, you can't possibly do this task. The planet's so small, the photon noise is so large. So you're going to use every trick you can think of, and you're going to have to dig the signal out of the noise. So let's think of the first trick being, let's put ultraviolet filter or sunglasses on our system, cut out the ultraviolet light, and now here's our same star. Now it's much quieter. Nevertheless, it still has spots. They're as big as a planet. It has plages, those bright areas to your right. And again, that means the star is variable. It's always brightening and dimming and helping hide that little planet as it crosses it. But one of the things that's special is those spots are, first of all, attached to the star. They take days, weeks, months to cross the star. A planet zips across in a few hours, and it's very, very repetitive. It'll often repeat the orbital period to part in 100,000. Spots don't do that. They come and go at random. So that's going to help us. We're going to look for several transits, which means we're going to have to look for several years if we're talking about planets in the habitable zone of stars like the Sun. And that's going to help us distinguish it from spots. This is what we used to try to sell this mission years and years ago. Before anyone knew how variable the star was, except for the quite variable stars that were too variable to be of interest. This is the Sun. These are measurements by the SMM satellite in the 80s. And basically, we have several different measurements. You might measure the output of the Sun over a period of some 250 days. And so you can, let's go ahead and fix this. This is the measurement of the actual Sun over a period of 250 days. You can see it wobbling up and down. Here's another measurement, another separate measurement. And what I've done is I've taken the data and I've subtracted a little bit of light like the Earth was crossing the Sun. And that's shown right here. You say, if somebody showed that to you and said, that's proof that they're Earths, most of us wouldn't find that convincing. But what if you did it over and over again and you saw it there and there and there and there? Well, you could add up all the data. And when you did that, the noise would add up as a square root of the number of times you did it. But the signal is coherent. So it would add up linearly, and you would see this. This is enough, so a computer searching through 100,000 stars, 170,000 stars would say, you found something interesting. Let's call it to the attention of the people who are interested in this, and they will look further to see if this is really valid. So that's what we do. We do not know what period this is going to be. This one is set up at a period of 250 days. Well, it could have been 251 or 147.3, so a supercomputer runs through something in the order of 100,000 possible orbits for every possible star, and then calls our attention to the ones that look like they may very well represent a planet. Here's our instrument. It's basically your camcorder. Your camcorder could do this. It just needs a big telephoto lens, a meter in diameter. It needs to be in orbit. It needs to be extremely stable. But basically, that's what it does. It takes pictures every 6 seconds of one field of view, adds those pictures up of each of these stars, stores it, and sends that back to Earth for our analysis. And so it's going to observe for several years, so we see several transits. It's going to monitor a single large area of the sky, because you don't want to miss transits. You need 3 transits, and if it takes a year per transit, you miss one, you're going to have to look for an additional year. And so it's going to look for several years looking for this planet. It's going to be in heliocentric orbit. Spacecraft does not orbit the Earth. It orbits the sun, just like the Earth does. And that means there's no day, there's no night. It looks at the same stars 24 hours a day, 365 days a year. And it works hard at not blinking. We add up to 30 minutes. We add up these frames to 30 minutes, send it back to Earth every 30 days to look at that. Because transits are generally several hours long, so a 30-minute cadence is quite good. But there's some 512 stars we look at with a 1-minute cadence. And that is, since we know some of these stars have planets, we found them, we can measure the exact period of orbit, see if it moves back and forth a little bit. If it does, that's giving you a measure of the mass of the planet. Not just the size, but the mass. And that's quite important. It's also allowing us to do astroseismology. These stars are pulsating. They're pulsating like the Earth pulsates. Every time there's an earthquake on the Earth shakes. The echoes go through it, and we can use the echoes on Earth to tell that it has a core, that it has a mantle, it has density variations. Nobody's ever dug down to see if it really does have a core. Use these pulsations. Similarly on stars, you can use the pulsations to tell you how big the star is, to 2%. That's great, because now you can know the size of the planet to 2%. Most stars you only know to about 25% in size. And so you only know the size of the planet to 25%. So huge help there, as well as a chance to look into the stars themselves. So what we see here is the instrument. The instrument is a Schmidt-Taut kind of telescope. Here is the corrector, a lens here. Light comes through here, hits the big primary mirror, and is focused over here on all the detectors. This is the detectors. In your camcorder, your detector is about 1/4 inch. This is a square foot. And this is so curved, the surface is so curved, it's by no means a focal plane, it's a focal surface. And you can't focus these the images on this because the CCDs are flat. So you put lenses over every CCD. This is a square foot of sapphire that covers these detectors to flatten that field just before it's focused. We have 4 fine guidance sensors. These are little CCDs in the corner that track the stars. They each look at about a dozen or so stars. And they hold the field of view perfectly on those stars. Now it can't be absolutely perfectly. It can hold it to 100th of an arc second, 3 sigma, for periods of half an hour or so. But difficulty is, this spacecraft is moving at a fraction of light, like the Earth is. And consequently, the star field changes shape a little bit. As you rush toward the star field, it shrinks. You move away, it expands. So the stars, the universe in some sense that you measure, is expanding and contracting, and we see that motion, of course, and have to compensate for it with our detector systems. Over here, we have the different responses, the spectral responses of the lenses and the detectors and so on. But when you put that all together, you get the black curve saying, this is where it's responsive. 430 nanometers, which is the visible. Start at the visible, down here to the infrared, a little bit past what a human can see. But this cutoff here cuts off the ultraviolet that we talked about. And so we do get rid of that radiation to try to quiet our stars, the stars we look at. The mission started on concepts many, many years ago. In construction, it started in 2001. And we worked, there was 2,000 people that built this instrument, built the spacecraft that controls the instrument, and this is its launch. This is a launch after several years and $600 million of work to put this together. It's a Delta II, the most reliable rocket that the U.S. has. At the top of that pod there is about the size of the VW van. That is where our instrument, our spacecraft are. That's what gets launched in orbit, a 3-stage system here. It was just a lot of work. It was very exciting. It's a nighttime launch. Everybody's excited. 2,000 people are there watching this, hoping this goes into orbit rather than into the ocean. And it was just exquisite. It was just exciting to see this launch into orbit. It was one of the most exciting nights of my life, but my wife says it really wasn't. So, nevertheless, the spacecraft did get into space, and it's now in a 53-week orbit. 53-week orbit means that it gets further and further from the Earth. Each year, it's a week further away. And that means the data rate goes down. At some point, of course, we run out of fuel, and the mission stops. But what's interesting is 53 years from launch. That was 49 years ago. The Earth will lap this. It will be back near the Earth. And my hope is that people here, the young people and their children, will continue to develop mankind's capability of going into space and go out there and pick up this telescope. It'll be historic. It will have told us what Earths are common or rare, and put this in the Air and Space Museum. And if people are really on the ball, I expect the Air and Space Museum, or at least a branch of it, to be on the moon. So, you know what I expect. Okay, we have found, as Andre mentioned, over 3,000 candidates. These are things that we really believe, signals that we really believe are planets. Well, something like 10 or 20% of them won't be, but we go through these one by one to confirm them. Actually, last 2 weeks, we've gone through 44 that we've announced as candidates. They're not on here yet, but this gives you a feeling for what we're finding. These are all confirmed planets, where we've done all the ground-based work to say, this is not a double star, this is not a small star crossing a large star. You know, it really is a planet. And when we look at that, what you see are, here is Jupiter for size. There is Neptune. Where's Neptune? Neptune is right there, and there's Earth for scale. And we have a lot of planets at all sizes, but look at this group here that are bigger than Jupiter. They can't be bigger than Jupiter. If you go look at your textbooks, that's the biggest possible planet. If you take Jupiter and you throw a brick in for some extra hydrogen, or you throw something small like the Earth in, it all falls into Jupiter, dissolves, and Jupiter doesn't get bigger. It just gets denser. But that's not what we find. This is a surprise. This is something, in some sense, that wasn't predicted, a feast for our theorists to think about. And so these are quite a bit bigger than Jupiter. Sometimes the densities are very much less than you would have guessed. The density of some of these objects, the density of an object, you know, I'll just, God knows how many trillion tons, is less than the styrofoam, the average density. Really surprised. So how could that happen? One of the things is, of course, that this big planet may have winds in it, just like Jupiter does or Saturn. Very strong winds, but they're deeper down. If they're deeper down, they're hotter. If they're hotter, they can be ionized. If they're ionized, that's an electrical current flowing around in the magnetic field. And so that generates other currents that might, in fact, heat the planets and put the heat in the core of the planet, keep it expanded. So that's one possible explanation. Another thing to look at here is we're finding planets now smaller than that of the Earth. And we'll show more of that as well. So we're getting down to small planets, but they're not necessarily in the habitable zone, where you need orbital periods of months or years. Okay, let's talk about the candidates themselves. And then this shows the candidates that we found as of February of earlier this year. In October, which is coming right up, we'll have another 500 or 600 to add to this, but I don't expect the dependence will change substantially. We'll probably build up smaller ones because they're harder to find, they take longer to find. But we're finding 246 Earth-sized planets, up to 1 1/4 size of the Earth. 250, about twice the size of the Earth, up to twice the size of the Earth. Then we find the planets that are some mixtures like Neptune, and the planets that are gas giants like Jupiter. The difficulty, of course, is that this is what you observe. It doesn't mean that's what's out there, it's just what you observed. You know that you missed a lot of it because the orbits didn't align properly. And so if you try to compensate for some of that, this is an example of trying to compensate for some of those factors. It's not a complete compensation, but it's an important effort that we did earlier this year. And what we have is the size of the planet. Here's 9.6, 12.9. Jupiter's 11. Neptune's 4. Earth is about 1, okay, by definition. Now, when we first saw this, what we saw, of course, was the early giant planets. They're easy to find. And so we saw all these points. You run a nice, smooth curve right up here, and that tells you how many small planets, how many Earths there should be. But that's not what we're finding. We're finding these smaller numbers. It does follow that curve. The curve breaks. Well, what do you make of that? You know, it's not just numbers, it's not just distribution. What does this tell us? well, one of the things it can tell us is, imagine that we've got this dust and gas disk, and we're trying to form Jupiters. To form Jupiters, you're going to start out with rocks, and you're going to build up planetary embryos, that they're called, that are maybe 10 times as massive as the Earth, 15 times as massive. When they get that massive, that gravitational potential so high, the gas, the hydrogen and helium, condenses on the planet. And all of a sudden the planet grows, expands dramatically to form Jupiters and so on. So that's what we're having here. And in fact, at some point, the star lights up, blows away the dust and gas, game's over. You either became a giant planet or you didn't. That hydrogen and helium is gone. So these are the ones that got very large, and there were many that didn't quite make it. And this group probably is a group that didn't make it at all. It was an embryo, it got no dust and gas, it didn't catch up fast enough. And so what happened when the dust and gas is gone is all of a sudden the planets don't see that disk, they see each other. And they start scattering. And so they crash into each other and they build the rocky planets. They build a planet like the Earth, which after all was a planet that was struck by another planet to form the moon. And so what we're seeing here are two mechanisms. The mechanism of the giant planet formation and the mechanism for the rocky planet formation. Again, that's the interpretation. As we get more data, you may see other explanations. This is an interesting figure. What you've got is the orbital period and horizontal axis that's logarithmic. So you see 1, 4, 10, 100, and far to your right would be several hundred days like an Earth year. Vertically, you have the size of the object. Earth size, 1, 4 is Neptune size, 10 is, or 11 is Jupiter size. And the colors are telling you, as we get the data, we analyze the data and we deliver the data to the public, and we publish that. And what we see is that, first of all, the blue points. Up to when we published our data, everybody thought most of the planets were Jupiter planets, because that's all they could find from the ground. But what we saw immediately was not only were they not Jupiter planets, Jupiter-sized planets, they weren't even Neptune-sized planets. An awful lot of these were smaller than Neptunes, which is great, because we're interested in small planets, not the big ones. In February 2011, the red data, and you can see all of a sudden we're beginning to see planets quite a bit bigger than Jupiter and some smaller than the Earth, and some planets toward the longer orbital periods. The latest data set, the yellow, again, lots of planets smaller than Earth, and planets more with longer orbital periods. That corner in the right, lower right here, that's the spot of interest. You're interested only in the smallest planets. You're interested in only as longest orbital periods. And each year, as we get more data, we get more transits, we can find smaller planets, we fill this in. First of all, the blue we had this, the yellow we have this, so we're moving in that direction. And as the years go on, you should see that fill in and get the answer, are there Earths? Well, we talked about small stars, big stars, and intermediate stars. And the orbital periods in the habitable zone will be short for the cool stars. Well, here are planets that we're finding planetary candidates in the habitable zone of their stars. These stars are generally cooler and smaller than that of the sun. But we have about 50. These objects are in their habitable zone, and this is their temperature. Now, the temperature is not the surface temperature. We can't measure that. The instrument cannot do that. But what it can do is tell you what temperature the atmosphere must be radiating away at to match the heat that falls on the planet. And so what we've done here is put the Earth is on this dotted line, and we say, well, if the planet had an atmosphere similar to the Earth, which would raise the surface temperature up about 30 degrees, which of these planets could have temperatures between the boiling point, the water, and the freezing point at the surface? And this is the group, and we have something in the order of 50 here. One of them, by golly, is Earth-sized and right here. Unfortunately, we have looked at that data in the last couple of weeks and found the star that is around is a bit bigger than we thought. It's a bit hotter than we thought. So now its temperatures are well above boiling, and in the coming weeks, I will clean that up and move that off the chart. So the chart is something that constantly undergoes revision. But one of the things you notice is there are no Earths in the habitable zone. There are some things that may be super Earths up here, and we have bigger planets and planets up Jupiter size. Well, we're not going to find any life in Jupiter. Jupiter's a gas bag. But Jupiter has moons. Our Jupiter has moons. It has larger moons. And you can imagine these having moons like in the movie Avatar, Pandora, moons as big as the Earth, with atmospheres, maybe several of them, and people go from one to the other and visit relatives, or they go shopping, or go on vacation. So every one of these objects is of interest to us, and we're working at taking the ones that we have our best data for and trying to confirm them as, for sure, planets. Here's the first one that we've confirmed. This is Kepler 22b, and it's in the habitable zone. You can see that it has a size about 2.4 times the size of the Earth, which is a little bit big. It's probably a water planet. It's probably not a rocky planet like the Earth. But we'd like to measure the mass as well. We got the size, but to measure the mass, you need a radial velocity. Well, the orbital period here is 290 days. Radial velocity measurements are just about impossible, but not impossible. So we have the Keck telescope making measurements. We have Hartz North, one of the best brand new spectrometers, came online in April trying to determine the mass so we can find out, is this rocky? Does it have a density of 5.5 grams per cc like the Earth does? Or is it closer to Saturn? Water, 1.0. So we don't know yet. One of the things that we like to do is, again, interpret what we have found. What are we learning from it? Here, what we've taken are all our candidates, we broke them up into 4 groups. Earth size, super Earth size, Neptune size, Jupiter size. And said, well, here's the distributions. What is the meaning? What is it telling us about these systems? Well, first of all, we see that all the numbers fall off dramatically as you go to longer orbital periods. That's the same thing as saying as larger semi-major axes. And if we think back as to what we were talking about earlier, imagine for a moment that the number of planets is constant with distance, with semi-major axes. Would we see a constant level curve? Of course not. The probability that you would see the planet is inversely proportional to the semi-major axis. So you'd expect the fall even if it was constant. So we can understand what we're seeing here, that it is not constant, it's less than constant, in fact. Well, that's interesting, we understand that. Well, what about these peaks? There's a peak here at 3 days, 3 days, 3 days, and 3 days. Why is that? Why should planets like to have an orbital period of 3 days? Well, imagine that the planets are migrating inward, and they're going to fall in the star, and at some point they're getting near the star, their orbital period is around 3 days. These planets are molten. They are glowing like like molten iron, actually. So they're liquids. They are raising tides on the star is raising tides on them. The star is young. The star is rotating very rapidly because it had all that angular momentum that it picked up from that cloud that it formed from. And so as long as it's rotating faster than the orbital period of the planet, the tide on it can add angular momentum to the planet and give the planet the ability to stay in that orbit, to park in that orbit. Keeps giving it angular momentum. At some point, the star lights up, blows away the dust and gas. The planet no longer makes a wave. It's no longer losing energy. That parking orbit becomes its orbit. So that is a possible explanation. There are other explanations, but it's certainly one of the ones that is a typical explanation for why we see so many in 3 days. Well, what about the other guys? Look at this one. It's got 20-some planets well inside that. 2-day orbits, 1-day orbit, even less. Again, 15 here, another 15 here, and again, another group here. How did they come about? It could be, they came spiraling in, and just about the time they were to crash with the star lit up. The star blew away the dust and gas, and now they were in stable orbit. Well, the probability of that, I think, is really small. But imagine instead that we had planets in a parking orbit. Huge numbers of planets in a parking orbit. At some point, the gas and dust is gone. Does that mean the tides are gone? The tides are still there. That planet is still liquid. It's raising tides in the star and vice versa. But now the star is slowly losing its energy. It's losing its rotational energy. It's giving off winds. And finally it slows down, so its rotation rate is less. Its rotation period is larger now than the orbital period of that planet. Now it's the planet's turn to give up its momentum, to give up its energy, and continue its descent into the star. So I think that's what we may be seeing. We're seeing planets on their way into their stars. But we don't know. Something to continue to monitor. We talked about planets orbiting stars, but we're interested in planetary systems. And we find, this is actually updated a couple days ago, we've got 387 transiting multi-candidate systems. We need to, oh, that does look a little bit blank there. Okay. Ah, thank you. Okay, so people don't have to imagine quite as much. So what we have here is a system that we found. 6 planets orbiting a single star. The orbits, if you project them down, are within the orbit of Venus. So these are extremely hot. 5 of these are inside the orbit of Mercury. So the temperature of these planets are, if not molten, extremely hot. Well, we know from that picture, right, that if you form planets close to the star, they're going to be refractory. They're going to be Mercury, Venus, Earth, and Mars. They're going to have a density like Earth, 5.5. Well, we can measure, these are so close to interact with one another, we can get at their masses, we can get at their densities, and the density of the innermost one is 3.1. That's not a rocky planet. That may be a water planet with some extra rocks and so on, but it's not a rocky planet. That one isn't either, and these have densities less than water. These planets, which we would have predicted would be rocky, are not. Furthermore, if you look carefully at things like, oh, this planet is 2.6 times the size of the Earth compared to that one at 3.5, which is bigger, and so this one, which is smaller, ought to be denser. It's the least dense. This one is a little bit bigger, so you say, well, it's going to be a little bit less dense, and it is, but not by factor 3. So all these planets are telling us, we don't understand. We cannot predict what happens when these planetary systems form. So a lesson for us to think about as we develop our ideas about the formation of our own solar system. This is a picture of Luke Skywalker going out to do evening chores. We've modified the picture a little bit because when you looked at the picture originally that George Lucas put together, there was a factual error. Now, clearly, the star that's white and big and bright is the white star. The little star is the cool red dwarf. Now, Lucas got it wrong. He got the colors reversed. So we called him up and said, look, George, you made a mistake in Star Wars movie, and he enjoyed the humor. And shouted his press crew to come and join us with our press conference. But here is an example now. Not of a planet orbiting a star, but a planet orbiting a double star. These are 2 stars, the planet orbits both of them. This particular one is the first planet that we found orbiting a double star. And that's interesting because, of course, when you look up at the sky and say, well, look, that's a star tonight. No, most of those stars are double stars. About 50% of them are double stars, or triple stars, or quadruple stars. So this is something we might ask, is it common? This is actually not a good place to look for Luke Skywalker's home, in that the planet's too big. It's 8.4 times the size of the Earth, so it's much more like Jupiter. The density is less than water, and the temperature at the top of the atmosphere is minus 126 Fahrenheit, and not even in the Antarctica do you get quite that cold. Pretty close, but you don't. So we need to continue to look further. Okay, so we've looked further. We found quite a few of these systems where we have planets. This is not a planet orbiting a double star. This is a planetary system orbiting a double star. And so you see the double star again. We got the colors right. The big one is white, and the small one is red. Here's the inner planet. There's the outer planet. This outer planet is the habitable zone of that star. Now again, it's a little bit big, 4.6 times its large 303-day orbital period. So it probably doesn't have any life on it, but if it has moons, they could have life. And we are searching for moons around these objects. So I don't think that's, again, Luke Skywalker's home, but we certainly are continuing to look. I'm going to give a few minutes, a very brief outline of some of the things that led to the mission, if the system will allow me to. Basically, this got started a long time ago with an idea in 1971 by a fellow named Frank Rosenblatt, who then went out, had a canoe accident, died. several years went on, a decade went on, some of us got together and decided we would see if we could make it practical. And we generated various kinds of photometers. And in 1992, we were ready to propose our first photometer for a space mission. It got rejected. People said there were no such detectors that could find tiny planets. In 1994, we reproposed, and they said it was too costly. It's like the Hubble Space Telescope. Notice that in 1995, the first planets get found. So we're proposing years before that, and of course that made it difficult because no one knew there really were planets. But that year, 1995, we did show CCDs could do the job if you measured and corrected for their systematic errors. In 1996, we reproposed, in this case Dave Koch and Carl Sagan, who was a member of the team, Jill Tarter, you probably remember Jill Tarter from Contact, were part of our team, and they suggested we change it from FreeSip, a really great name that I thought of, to Kepler, just because Kepler was a German scientist, a German astronomer who thought of the laws of planetary motion and optics. So yes, we did that, but we still got rejected. And they said, really, that no one has ever done automated photometry. When you do photometry, you do one star at a time. You're talking about doing automated photometry and thousands of stars at a time. So they rejected it and said, well, go build an observatory and show it can be done. This is our observatory. We built that the following year at a there's some small telescopes there, and it wasn't completely automated, so we actually had observers. One of our observers was Spock here. He had some unusual habits, and so he wasn't always welcome. In particular, he really liked feasting on wires. Now, that's what makes the telescopes work, so he wasn't always welcome. We did that. That was successful. We showed you could do automated photometry. And they said, well, great, that's marvelous. Your proposal rejected anyhow. Go build a facility in the lab that can do 10 part per million photometry and show the very small changes in light, detect them like a planetary transit. So that's what we see here on the left-hand side, about 10 feet tall. The bottom is a light source that lets light up through a panel with a bunch of holes drilled in it that represent stars. Above is a little telescope. We shake the telescope just like the spacecraft shakes on orbit because the reaction wheels aren't perfectly around, so it does move, and we were able to show indeed we could do this. On the right-hand side is a very complicated pattern, but basically it shows that by injecting these motions, we can measure them and correct them and satisfy people that this is technically ready for a space mission. Kepler will end. Kepler's been extended for 4 more years, but it will end. It's got some little problems. And it will end. And so the question is, well, what's next? The National Academy of Sciences said, before we pick the next big mission, we want to have the answers from Kepler. Are there lots of planets or few? If there are a lot of them, then we're going to build a coulter or a coronagraph to go and look at the atmospheres of these planets. If, on the other hand, there are very few, then we have to use an interferometer. Now, the other instruments, the coulters and things like that, are very expensive. Billions of dollars to build one of these. The interferometer is extremely expensive, not just very expensive. And so we don't want to choose that until we get these answers. Once we have the answers, you can imagine several instruments that could be useful. This is a simple example of one. Basically, you've got a space telescope looking at this star. You believe the star has planets on it because you've looked before, but the star overwhelms the light. So we have a coulter. This is a disk 30 to 100 feet in diameter, thousands of miles away in orbit, and when you look at the star, this coulter moves in the way and blocks the light from the star, so you can't see the star. But you can look over the edge and you can see the planets. So this is a way now of blocking the light from the star and looking at the light from the planet. So what's that useful for? Here's a possibility that's a simulation. This is Alpha Centauri, the closest star to our solar system, and this is a simulation. All the brightness here is all the dust the comets make and things like that. The solar system just lights up. And so here's a simulated Earth, and we could get spectra of that. If the spectra looked like this is a wavelength along the bottom, brightness at the top of the planet, not of the star. And we saw a nice smooth curve. It's a hot rock, no atmosphere. But what if it has a dip here? It's got CO2 in the atmosphere. dip here, it's got water in the atmosphere. That's what you need for life. That's what plants live on. If plants have lots of surplus oxygen, the oxygen will form some ozone, and the ozone will warn us that atmosphere has got oxygen as well. It's a great atmosphere. Well, of course it's a great atmosphere. That turns out to be the spectrum of the Earth's atmosphere. And that's what we're looking for. Do other planets have such atmospheres? Could you do anything else? And the answer is, if you build a mission even bigger than that, with a big telescope like they're beginning to build on Earth, 30 meters in diameter, you could look at the Earth. You could look at a planet. Here's an example over one day of how the reflected light would look from the Earth. Here it's dark. You're looking at ocean. Ocean doesn't reflect much light. Here you're looking at land, and you're getting more reflected light. Some more ocean here. And so that's what it would look like if you looked at the Earth. If you lost the ice on the poles, it would look a little bit different. If it was entirely ice-covered, you wouldn't see this curve. You'd see this other curve. It would tell you you've got an ice-covered planet. Here's another set of curves. Again, the Earth for reference. Here, if the planet was all desert, that's a lot of reflectivity, you would see this instead. It would look a bit different than that. You might tell them apart. If the planet had dinosaurs or had lots of vegetation, jungle covered, it would look like this. So by looking at these different curves over time, the photometric curves, you could tell quite a bit about the planets themselves. So this is what I think the future holds for us. We need to move on and go ahead and build these instruments. Thank you for your time.
Ladies and gentlemen, before I open the floor for questions, I just want to mention that Kepler and Bill Borucki have won many prestigious awards. I waited for this presentation to be done. I just want to mention 3. The first one was in 2009, the Most Brilliant Innovators Award. You can see why. We asked Bill at dinner last night what kept him proposing for Kepler. You saw that Bill started in the early 90s. And he said, well, my colleagues may say perseverance, I would call it stubbornness, but this is what it takes. In 2010, Bill was awarded by the New York community the Lancelot Berkeley Award. And just recently, in 2012, there's been a Mullman Award that's awarded by the Astronomical Society of the Pacific. And these are just scratching the surface. Kepler as a project had won the best software award, the best web page award, and so on and so forth. So I'm really trying to convey how much success Bill had brought to the scientific community in general and astronomical community in particular. And with that, I would like to invite questions for Bill. Yes?
Do you believe that there's life elsewhere?
I'm sorry, I didn't hear the question.
Do you believe personally that there's life on other planets?
When I look at the conditions that life exists in our own planet, you know, I'm living in rock, under the ground, in boiling springs and so on, and I can imagine that those conditions exist in a lot of these planets. It certainly wouldn't surprise me, but it would be just speculation. It certainly wouldn't surprise me to see a lot of life in our galaxy. In some sense, I'm a little bit surprised SETI hasn't picked up a signal yet.
Yes? Right here.
If you do find a planet that you strongly believe could sustain life, what do you think the next step would be?
I'm sorry, I'm having a hard time hearing you.
I'm sorry. If you find a planet that you strongly believe could sustain life, and you really think that there is life on this planet, what do you think the next step would be you would take it?
That's, you know, what you're saying is, do we ever, what would be the next step if we found a planet that we believed life existed on?
Yes.
That is something that, in some sense, is a bridge too far. In that this is a discovery mission. It takes the best of our technology and reaches out into the galaxy and asks, are there Earths? But we can't tell whether they have atmospheres. And if it had atmospheres, we would know that whether it had oceans, and we would know whether it had life. Those are experiments that would be done by you and your children. We don't know, we do not expect to find any evidence because we do not have the instruments that would allow us to detect it, even if we're covered with life. So it's, there's no future mission yet, because even the missions I described are missions, let's say that you found oxygen in the atmosphere. What would that prove? That there might be life. That's a different story saying there is life. So we've got a long ways to go before we know there's life. Even on Mars, which is just next door, it takes an enormous effort of putting rovers down to try to find life. So we've got a long ways to go before we can answer your question.
Bill, on the slide that you showed, the average densities of a planetary system around one of the Kepler objects, what was your argument for why the innermost one couldn't be rocky? It had an average density of 3.1 grams per cubic centimeter.
That's right.
Couldn't it be a silicate-rich body that had not differentiated? And so, that's just its average density of rock. I'm not sure.
People build models of these. They put a core in, they put silicate rock, and they put water on, and they ask, under what circumstances could we look at some of these things and explain them? And here they generally say the density is just simply too low. But it could be, as you're saying, there's rocky material, there's water material, but there's a lot of hydrogen helium. So it's a planet, but probably not a rocky planet. A rocky planet, you've got to get rid of the water, which is low density. You've got to get rid of hydrogen helium, which is low density. Otherwise, it's not a rocky planet. So the thought is these are not rocky planets. They're interesting planets, but they're not rocky like you could walk on them.
Any other questions? Yes, in the back. Can you wait for the microphone, please?
I can. If you could describe the most exciting moment of looking at the data. If you could describe the most exciting moment when you're looking at the data, when you're investigating other planets and their...
Well, certainly one of the most exciting times with respect to data was the spacecraft goes into orbit, it gets commissioned for something like 40 days. It's covered, the cover is closed across it. We know the internals work, we know the various amplifiers work and the temperatures are about right. And we blow the cover off and we look, will we get an image? Will the CCDs get the right voltages? Will they output properly? And all of a sudden we see the whole sky light up with just tens of thousands of stars. That was an extremely exciting time. And of course, when we began to get some of the data from the stars, so we had time series, all of a sudden we could just look. Jupiters have such big signals. You could look at, oh, there's a Jupiter, and there's a Jupiter. So that was very, very exciting. But actually, much of what we see in this data, we get data for 150,000 stars. You've got to paw through it all, looking for things that are particularly interesting, and asking yourself, can I believe it? Will the ground-based telescopes prove this out? So I think that's probably less exciting than what we saw before. But what really is exciting is when you get a paper accepted. It really is exciting because it says you have proved to your colleagues that this is true. This is good data. This is a good result. That's exciting to see the acceptance.
Yes, Bob. Can you wait?
One number that could help put some of this in perspective would be, what's the light travel time to, say, the nearest star where you've identified a planetary candidate like Earth? How long would it take light to come from that star to us?
Okay, so how long does it take light to get from the stars to us? What's the light travel time? What's the distance in light years, in some sense? A survey like this looks at all the stars that look like there could possibly be sun-like in some sense. So it looks at some of the dimmer, redder stars, which are always closer by. Because otherwise, if they're very far away, they're so dim we can't see them. And similarly with the bright stars, if you've got a bright, hot S star, you can't look at it when it's close because it saturates your system. So you've got to look at it, to kiloparsec. So it's magnitude limited. And so we see some stars, some red dwarfs, some M dwarfs, things like that. I think our closest is about 30 light years away. So we have a few 30 light years. Most of our stars are about 1,000 light years or a few thousand light years away. We don't have anything that's really, really close. This is basically a probe out into the galaxy. It's not looking around the sun.
Yes.
Would it be possible, since you said that it's going to rank to the, could we search the Alpha Centauri system for the Vesta system for planets, or have we?
So your question is, could we look at some of the nearest stars and search them for planets? Like Alpha Centauri, I showed Alpha Centauri here. People have done that with a Hubble Space Telescope with their fine guidance sensors and things like that, because they would see motions of these planets. And they've looked very hard for several years. They have found no planets. That doesn't mean there aren't any, it just means they're smaller than, or they don't exist, one or the other. My guess is they're probably there, but they're just too small to find. Photometry, as I say, is a terrible way to pick out stars and ask about this. But there are other ways that are better. SIM was an instrument that was being developed for years. It's an interferometer. And it can see a planet, whether the orbit's perpendicular, toward us, whatever direction. It was so much of a state of the art. Ultimately, it didn't get funded. It may get funded again someday, but that would allow the nearest stars to be examined. Similarly, some of these big missions that I talked about, terrestrial planet finder, with these huge interferometers that would have many large mirrors in orbit, Earth orbit, Jupiter orbit, someplace out there, that too would look for these small planets around nearby stars, not far away stars. So there are such missions. We haven't flown them yet.
Yes.
Would you say that finding a couple thousand candidates in like only 3 years is a lot of planets?
It's certainly a very rich reward. It's just an enormous reward because there's a huge variety of planets. And we not only found planets, we found all sorts of things that we could not imagine. And so it's been a very rich reward. But is it what I expected? No, I expected more. I really expected at this point we'd be at the 5,000, 10,000 planet count. We're only at 3,000.
So would there be a lot more Kepler projects or Kepler-like projects?
No, there will never be another Kepler. No, I'm not being facetious. In that you made the measurement, you've got these frequencies, you go on to new things. You don't repeat. And so there will never be another Kepler. The next missions, such as TESS, which is being evaluated right now to see if they're going to fund it, is a mission that would launch around the Earth, and it would look at all the nearest stars, the brightest stars, and see do they have planets. Because then you could point the next missions at the nearest stars. We can't tell you about the nearest stars. We didn't look. We only looked as a probe, a simple first discovery mission. So TESS, or the European version is called Plato, would give you that kind of information, but it will not be a repeat of Kepler.
Did we learn anything about the planets that are too small to be picked up by Kepler? Like, can we infer anything about them from the data we have about the larger planets?
I'm missing your question. We're certainly looking at small planets. Some of these planets are smaller than the Earth. Many of them are smaller than the Earth, actually. And we're certainly seeing them as small as Mars. But what is it you're asking about these small planets?
Well, I'm saying that we're looking up down to a certain size. We can't just pick up planets smaller than that. But can we infer anything about their properties or something new that we didn't know before Kepler?
Before Kepler, we didn't know they existed. I can prove to you, let's go back a few years. We found some Jupiters from ground-based telescopes. The first Jupiter was found with an orbital period of 4 days. How did it get there? It came spiraling in, and it wiped out everything in its path. There was an Earth, a Venus, a Mars, they were gone. So clearly we were finding these Jupiters with short period orbits. There must not be any small planets. They've cleared them out. There are no small planets. Right? That's what we knew. That's what we thought. Now we know that's not correct. It happens, but the small planets appear after that, or they appear when there aren't Jupiters. So we're learning a lot about the existence of small planets and what stars they exist around. Now, are we trying to understand their densities? Sure, we're trying to do that, and I think in the coming 6 months, you begin to see some papers where we're getting at the densities of some of these. Our first small planet was 1.4 times the size of the Earth, orbital period 0.9 days, density 8.8. Now, those of you who know your metals, iron is 8.0, so this planet is denser on average than iron, and it's more. So we're learning a little bit about these, but you're also saying we can only look down to a certain size. That's not true. We can only look down to a certain signal-to-noise ratio. So if you say, I've got a planet the size of Earth, can I see it? Well, tell me how noisy the star is. My signal's going to be bigger than the noise. If you say, well, it's about, you got an 84 parts per million signal like Earth around the sun, and then you say, well, it's got an orbital period of 10 days. Well, that means I see 36 of these transits every year. So the signal goes up to the square root of that number, so it's 6 times easier to find than the Earth would be to find. If, on the other hand, it's out further than the Earth, and I've only seen 2 transits, I don't see it at all. So it's easier to see a Mercury-sized planet than an Earth-sized planet if its Mercury is closer to its star and the star is quieter. So it's never a simple yes, no, this is the limit. It's this complicated thing that we're always operating at the level of the noise. And what helps us is lots of transits. Just as I showed where we were trying to find Earth with the sun's measurements, you're always operating at the noise level.
I read somewhere that among all the candidates that are being considered as similar to Earth, there is one such candidate like Gillies 163c, which has maximum probability of finding life there. What do you think about it?
You're pointing out there's a candidate that you think looks like it was suitable for life.
Has maximum probability to support life. I did today in Yahoo.
Which one are you talking about? There are several thousand.
Gillies 163c in the Dorado constellation.
Okay. People are finding small planets. Although you have to be careful. You really have to be careful. You want to look at data as data. Not what you want it to be, but data. Consequently, if somebody says, I found a small planet, how did they find it? The answer is, oh, they did radial velocity. What is radial velocity? It's the motion of the star back and forth, changing that. And that depends on just the mass of the planet. So I've got a planet of a certain mass. Is it a rocky planet? And it's small. If it's a gas giant, it's big. But you don't know how big it is. So if it's a radial velocity detection, they'll say it's small. Small in mass. I have no idea what size it is. Similarly, we can measure the size, but generally, we don't know the mass. So these two techniques work together, but they often don't see the same star, the same planet. So I have no idea whether this planet could possibly have life. It's too early. We're too, we're the first there. We're the first people on the ship going to the Americas, trying to find India, okay? And we find all sorts of strange things that we didn't expect. But it's early. We don't understand what we see at this point. And so I would never say any particular planet is highly probable to have an atmosphere and have life on it. They're interesting. They're hopeful. But I don't know whether I would certainly not assume there was life.
One last question, maybe?
I saw you had a chart of all the orbitals of the planet, like your length, and you're looking for orbitals that were similar to that of Earth.
Which ones were you looking at?
Yeah, something like this. And I see this chart, however, I don't see anything with relative to the size of the star. For example, a smaller star, you'd be looking for a smaller orbital because the radiation would be less and the habitable zone would be smaller, therefore you're looking for a smaller orbital. Did you consider that in your data? Do you understand what I'm saying?
I really don't understand your question. We've got a diagram here that shows what we have found.
Okay.
It does not show the stellar properties. I think you were asking about stellar
Yeah, it
properties.
doesn't show it relative to the size of the star. So do you understand?
To the size of the star.
Yeah, and therefore a smaller star, you'd be looking for a smaller orbital, correct?
That's right. So when we look at smaller stars, on Earth, across a smaller star is a much bigger signal than that Earth is across a bigger star. So there's a bias. You know, if you look mostly at small stars we found, Earth, you know, you might expect that because the signal was so much stronger. But if you're looking at mostly hotter stars, bigger stars, you might not find any Earths and say, well, there aren't any Earths. There are. It's just that you looked at the wrong stars. So your concern about the size of the star is important in terms of understanding these probabilities and these statistics. And I haven't shown that here. I just didn't bring those pictures with me.
Okay.
Have I answered your question?
Kind of, yeah.
Kind of. Okay. Well, better than zero.
What's the distance of the habitable zone as a function of
Oh, distance to habitable zone as a function, sure. I always like to show that little diagram.
Yeah, so do you have a chart?
Let's look at that diagram. Let's go look at the small stars at the bottom. These are the M dwarf stars, and these are some of the K dwarf stars. Very cool, quite a bit smaller than the sun. They might be half the size, even a quarter the size of the sun. So orbital periods in the habitable zone range from weeks to months.
Yeah, exactly. So do you have a chart that shows the size of the star relative to the orbital zone? Like, because you just showed orbital zones, and in that chart, but you didn't show it relative to the size of the star.
You're saying I have a chart, is that right?
Keep going forward.
Okay.
Okay. Yep.
Was that it?
Keep going.
Keep going.
Keep going. Yeah. No. Well, keep going. I think one more. Okay. So there you have this, but you don't have anything that shows it relative to the size of the star. If you understand what I'm saying.
That's right. I do not show the relative size of the planet to the stars.
Exactly. So
That would be
show
basically
that.
some other figures, and
Okay.
I ran a little bit long, so that clearly we had to talk about what you're looking for, because of course we generate all those things. It's just that you can't show everything. You show what we hope people will be most interested in. But sure, that's important, and we do look at that.
I will stop the questions at this point, but mention that Bill Borucki is here all afternoon, and we are meeting back at the astronomy department. The students had a full hour to spend with Bill Borucki to ask any questions, and if anybody outside astronomy would like to join us, you guys are more than welcome. Otherwise, I would like to thank Bill Borucki again.